We would like to find and sketch the fifth roots of I, which means we would like to find the distinct solutions to the equation z to the fifth equals I. And the best way to do this is using polar form. So if z is equal to r e to the I theta, then that means that z to the fifth is going to be r to the fifth e to the I 5 theta. So we want to set that equal to I. We should write I in the polar form also. I is equal to 1, that's the modulus of I, times e to the I, and the argument for I is pi over 2 plus 2k pi. So equating these, r to the fifth, e to the I 5 theta, that's z to the fifth, equals I, which is 1, I'll write the 1, times e to the I pi over 2 plus 2k pi. And equating these, we have two equations. R to the fifth is equal to 1, and 5 theta is equal to pi over 2 plus 2k pi. K is any integer. We want the positive solution to this equation, and there is only one real solution to this equation, and that is r equals 1. So our solutions will lie on the unit circle, a radius of 1, and theta equals, divide by 5, pi over 10 plus 2/5 k pi. Now pi over 10 for the sketching part, pi over 10 is 18 degrees, and 2 pi over 5, 2 pi is 360 degrees, so dividing that by 5 makes 72 degrees. So we're going to have an angle of 18 degrees, and then increments of that angle of 72 degrees. So let's put the solutions here, the sketch of the solutions, and we'll make the unit circle. So there's a unit circle. Whoops. How did that happen? And there's our unit circle. So this is the number 1, this is the number I, this is the number -1, and down here we have -I. So our solutions lie on this circle. R is 1. The first one has theta equals pi over 10. We'll take k to be 0. So that will give us pi over 10 for the angle. So that's about 18 degrees. Maybe that's here. So that's our first solution. Then we have to do 18 plus 72 degrees. Well, that's 90 degrees. So that's here, which means that I to the fifth is equal to I. That checks out. So that's one of our solutions to the equation. And then we need 90 plus another 72 degrees. So that's 162 degrees. And that should be right over here, symmetric with this. That's 18 degrees up from the negative real axis, and this one was 18 degrees up from the positive real axis. So here's another solution corresponding to k equals 2. This one was k equals 0, k equals 1. And now when k is 3, our angle is 162 plus another 72, because our increment here is, when we bump up k by 1, it gives us an extra 72 degrees. So this is 234 degrees, which is somewhere over here, k equals 3. And then when k equals 4, we have to add another 72 degrees to this. So that's 306 degrees. That's k equals 4. And k equals 5, we have to add another 72 degrees to that. That makes 378 degrees, which is the same as 18 degrees. 360 plus 18 makes 378. So k equals 5 is the same as k equals 4. So we're only getting 5 distinct roots. So z to the 5th equals I. There are 5 distinct solutions. The solutions can be written as 1 times e to the I pi over 10 plus 2k pi over 5, where k goes from 0 up to 4, 5 distinct solutions. And they're equally spaced on the unit circle, so if we draw these line segments here connecting the roots, then we get a nice regular pentagon. So a nice geometric interpretation of the 5th roots of a complex number.